Welcome back to our pre-class videos. Hopefully you're watching this probably on Sunday night before we meet on Monday morning. Hopefully everything works well with that live stream with Zoom. We'll see how it goes. If it doesn't go well, we'll have to try something else. But you should be able to watch this video, hopefully with no issues. So anyway, let's talk about the Wronskian of a set of functions. So in applications, and namely what I mean by applications in this sense is differential equations, it's useful to have a set of linearly independent functions. So we've talked about this a little bit in class. I know it's been a couple of weeks, but we have talked about this, that one of the fundamental principles of being able to solve differential equations is to find a set of linearly independent solutions that you know is enough of them to span the entire solution space, so that you can write any solution as a linear combination of those linearly independent vectors, in this case functions. So it's important in differential equations to know you have these linearly independent functions. So it's probably more information that you needed to know for this particular class, but I just wanted to give you an idea of why we care about checking such a thing. So in general, checking whether or not a set of functions is linearly independent can be a difficult task. In some certain scenarios, in particular, being able to show something is linearly dependent may be a little bit easier, but trying to show that it's linearly independent can be hard. So let's do an example here. So let's let S be the set of the functions sine squared x, cosine squared x, 2 tangent squared x, and 3 secant squared x. And we're asking whether or not this is a linearly independent subset of the set of continuous functions on the interval from minus pi over 2 to pi over 2. So remember that notation again here. The C just stands for continuous functions, and this is the interval on which it's continuous. If we have superscripted numbers here, that tells us the idea of being able to differentiate a certain number of times, and the derivatives are still continuous. Anyway, so in this case, we're going to take advantage of trig functions that we know, or trig identities that we know. So we see here that if I take 3 times sine squared plus 3 times cosine squared, and then do 3 halves times the 2 tangent, so that should be tangent squared, so a little bit of a typo there, and then negative 1 times 3 secant squared, I use trig identities, I factor out the 3 here, I get sine squared plus cosine squared gives me 1, and then here I'll factor out the 3 from the 1 and the tangent squared x. Notice the 3 halves times the 2 simplified to give me 3. And then again, trig identity 1 plus tangent squared is secant squared. So now when I subtract, I really do get 0. So what this means is that we found constants, not all zeros, constants here of the set of functions that give me the 0 vector, in this case the 0 function, in the set of continuous functions on this particular interval. So that tells us that that set is not linearly independent. All right. So that wasn't too bad. If you remember your trig identities, that wasn't too bad. But in general, you can see where this could be a pretty arduous task to be able to figure out whether or not it's linearly independent or dependent. In particular, you need to show that if you have a linear combination that gives you the 0 vector, you have to have all zeros as your constant. That could be a difficult task. So what the Wronskian is going to allow us to do is give us a computation that we can do to check relatively quickly whether or not a set of functions is linearly independent. So to start that off, let's suppose that we have a set of functions. I'll say they're f1 out to fn. These are going to be subsets of the n minus 1 times differentiable functions on the interval from a to b. So again, remember the superscript just tells us how many times we can differentiate. So we have n functions. Each of them we can differentiate n minus 1 times and remain continuous on the interval from a to b. Let's say that's a linearly dependent set. So starting with the assumption that it's a dependent set. From our definition, remember that means that we're going to be able to find constants, not all of them equal to 0, so that when we do that linear combination of these functions, I have to get 0, and it doesn't matter what I plug in for x, I always have to get 0 out. That's the important thing here, is for this to be linearly dependent, I would need to be able to use non-zero constants and plug in values for x. No matter what value I plug in, I always get out 0, like we did up here, right? We said that no matter what value of x we had here, we always got 0 out. That's why this was linearly dependent. It's not for some specific values of x, it's for all values of x. All right, so notice that if this is true for the original functions, if we differentiate both sides, it'll still be true, right? Because the derivative of the sum is the sum of the derivatives, and the constants just pull out for your derivatives, and the derivative of 0 on the right-hand side is also 0. So if a set of constants satisfies this equation to make this equal to 0 for all x, then that same set of constants will satisfy this equation where we talk the derivatives. And it'll satisfy it if we do the second derivatives. And it'll satisfy it if we do the third derivatives, all the way down to where we do the n minus first derivatives. All right, so this gives us a set of linear equations to solve. What we're trying to solve for are the constants, not the functions. We're given the functions, we're trying to solve for the constants. So if we think about this, we know if we're assuming that it's linearly linearly dependent, and I apologize for making the extra mark in here. If we assume that it's linearly dependent, then, stop touching the mouse, clearly. If we're assuming that it's linearly dependent, then we already have non-trivial solutions to this particular homogeneous system. Homogeneous because it is equal to 0 over here, right? So it's a homogeneous system. And we have non-trivial solutions because we're assuming there are non-zero values for the c's that work. All right. So what that means is that if it's non-trivial solutions, that means if I write this in matrix form, and in particular, if I concentrate on the coefficient matrix here, that coefficient matrix cannot be invertible, right? If it's remember, being invertible is equivalent to the homogeneous system having only the trivial solution. So if it doesn't have just the trivial solution, then it's not invertible. And again, this is true no matter what x we plug in, right? These are up here again with our equations that are up here. We know that this works, these have to be 0 no matter what we plug in for x. That's the important part. It's not for some values of x that make it 0. It means no matter what we plug in for x, it's 0. Okay? All right. So another way to check whether or not a matrix is invertible is to take its determinant. So if this is not invertible, then its determinant must be 0. So we notice the notation for this particular determinant here is w of x. Notice the columns here are your first function and then all the associated derivatives n minus 1 times. Second function, same idea. Last function, same idea. And notice we really do have a square matrix here, right? This is kind of like if you think about the 0th derivative, then we have 0, 1, all the way to n minus 1. That's n rows and n columns here. Okay, so this matrix, the w of x, is what we call the Wronskian of this. And what we just proved was, remember the assumption was that we said the set was linearly dependent, and we proved that if it's dependent, then this derivative is 0, no matter what we plug in for x. So the contrapositive of that is that if we have a subset of n minus 1 differentiable functions, if the Wronskian is not identically 0, meaning no matter what we plug in for x, we always get 0 out. If it's not identically 0, then we had to have had a linearly independent subset to start with. So this gives us a check for whether a subset is a linearly independent subset. So let's do an example here. So let's just look at two functions, e to the x and x e to the x. These are defined everywhere and can be differentiated as many times as you'd ever want. Okay, so it certainly could be on C infinity. Here I just want to check to see if these two particular functions are linearly independent. So first row is just the function, second row is just the derivatives. So derivative of e to the x is e to the x, derivative here, product rule. Okay, do your determinant, take your main diagonal, subtract your off diagonal, and you get the function e to the 2x. Well, in this case, it doesn't matter what you plug in for x, but in particular, this is not always 0. Okay? It's important. For it to be identically 0, it means that this x has to go away when you do the simplifying. Okay? So as long as there's an x in here, then that's going to mean that it's not identically 0. Okay? All right, so therefore, in this case, this particular set is linearly independent. So anyway, we'll do another example or two, and you'll see those in the homework, but I just wanted to give you an idea of what the Wronskian is to give you a little bit of a head start and to remind you of some of the terms that we talked about before we had our extended break. Hope everyone's doing well.